In my third video on magazines, I talked about this article on the new 50-watt amplifier circuit by McIntosh. In the course of that, I talked a lot about the new transformer and the cathode coupling that they used in this, but one thing that I omitted in the interests of time was why it was so important to find solutions to some of the problems with the transformers of the day. And one of the things that I would like to talk about now in this video are output transformers. The output transformer is fundamentally the difference between transistor amplifiers and tube amplifiers. So one of the design challenges that tube designers had to contend with, that you don't have to contend with the modern transformerless output circuits of solid state, is the output transformer itself. And I'm going to start by talking about this distortion at this point. Now, as you probably know, when you have a Class AB amplifier, one side of the output stage conducts in the positive direction, and another side conducts in the negative direction, and the handoff between the two is not always smooth. It produces what's called crossover distortion. Well, one additional complication in tubes is the output transformer also inserts a small inductive kick during this transition that is due to what is called leakage inductance. So I'd like to talk about output transformers, but especially I'd like to show you about leakage inductance, how you can measure it, and how you can model it in a circuit so that you can predict ahead of time how much this particular transformer is going to add in inductive kick. Now, I emphasize that even transistor AB amplifiers have some crossover distortion, but tube AB amplifiers have an additional distortion produced by the inductive kick that is modeled using leakage inductance. So first, we have to understand that the reason we even need an output transformer in a tube circuit is to provide impedance matching. The output resistance, or the plate resistance of the average output tube, is between 2,000 and 10,000 ohms, with 4,000 to 5,000 being a typical value. Speaker impedance, on the other hand, normally runs from 2 to 32 ohms, with a typical value being around 8 ohms. So what are the factors you can vary in the transformer in order to achieve this impedance matching and minimize the negative impact of a lot of other characteristics of output transformers? Well, one thing you can vary is the core material, both the core material itself as well as the size of the core material. And one thing that is true is you can produce some really good output transformers if you're willing to put enough of the right kind of material into the core. The problem is that the transformer very soon becomes so heavy that the amplifier is basically immobile. In fact, to really achieve a good 10 hertz to 100 kilohertz tube amplifier using core material alone and no special tricks with windings and other things, you need about 100 to 150 pounds of core material. Now, if you think about that, in a stereo amplifier, that would mean that the amplifier could weigh 300 pounds or more. Not a desirable thing for a piece of equipment in the average living room. Another thing, of course, is the use of wire size, the number of turns, and the number of windings. Now, I talked a bit about number of windings earlier. That is where, instead of having a single primary, you parallel several primaries. One of the complications of number of windings is, as you add windings, that increases capacitance. And as you increase capacitance, you kill the high frequency response. So here are the typical complications that you have to deal with. You have to deal with the weight issue. You have to deal with incremental inductance, which we will talk about in a minute. That is the fact that the BH curve is not linear, so that you start at 0 and you get what is actually an S curve. I'll show you one of those in a little bit. The third factor is one I just mentioned, shunt capacitance. That limits the high frequency response. And then finally, leakage inductance. And this is the one we're going to focus on mostly in this video. So let's take a quick look at incremental inductance and then move on to the real heart of this video. Here is what's called a hysteresis loop. It's a depiction of what happens in a magnetic material when you try to create a magnetic field. Now, the x-axis is actually the magnetizing force, but think of that as like the current through the coil that's wound around a magnetic core. And then the y-axis is the flux. In other words, it is the actual magnetizing, the magnetizing effect. You may notice that if you start at 0 and you begin increasing the magnetizing force or the current, the amount of magnetization that is produced doesn't go straight up in a linear fashion. It has a kind of S-curve to it. But what's even worse is once you reach this point, when you begin to remove the magnetizing force, you don't go back down that same curve and come out over here. Instead, because of residual magnetism, you actually follow this curve. And then as you get to maximum negative magnetizing force or maximum negative current, you're at this point, at which time as you increase it, it follows this curve. And obviously this hysteresis loop provides all kinds of distortion in the output transformer. Part of the reason for this is the residual magnetizing of the core itself. And so, depending on the core material you choose, this loop can be rather large and broad, or it can be a little bit more narrow. But no magnetizing material has an absolutely straight linear BH curve. In other words, as you apply current, you get exactly a linear amount of magnetizing in the core. This is one of the causes of problems in output transformers. We're not going to talk more about this. Instead, we're going to talk about another problem with output transformers called leakage inductance. Think about a transformer. In this case, I'm showing a transformer which has a tapped primary and an untapped secondary, but of course you can have taps on these to adjust. For example, on this side you might have the speaker, so you might have different taps. So for example, this might be for 16 ohms, you might tap the center for 8 ohms, you might tap this for 4 ohms, and so on. The typical push-pull tube output stage had a center tap transformer. Now, if you were using an ultralinear amplifier, you might also have a tap here for the screen grid. But we're going to take the simple case of an output transformer which has a tapped primary at the midpoint and a secondary that matches a particular speaker impedance. So what are we interested in knowing about this transformer in order to figure out how well it's going to work in our design? Well, one thing is the turns ratio. In other words, how many turns of wire there are on the primary and how many on the secondary, because that affects a number of things. And I'll show you in a minute how you can determine the approximate turns ratio of an unknown transformer. Suppose you have one in your junk box. You'd like to use it in a tube circuit, but you have no idea what its characteristics are. Well, if you have an inductance meter, you can measure that. If you don't have an inductance meter, you can actually create one using a function generator and an oscilloscope. I won't go into that, but there are several good videos on YouTube about that. In fact, I think both El Paso Tube Amps and John Audio Tech have talked about that in some videos. So you might want to look there if you're not familiar with the idea of using a sine wave generator and an oscilloscope. I'm going to show you how to do this using an inductance meter. But in the process, I'm also going to show you a characteristic you can measure with that same inductance meter that's called leakage inductance. And what leakage inductance is talking about is no transformer is perfectly efficient. Therefore, the current that you put in on one side produces a magnetizing effect in the core, which is transferred to the secondary, but not all of it gets transferred. There is some of the power that is put into the primary that doesn't wind up in the secondary. The difference between that is called leakage, and you can model that by putting an inductor in series that is equivalent to the leakage, in other words, the inefficiency of the transformer. I'll show you how we measure that in just a second, but let's look next at how we would model it first. Here is a typical circuit where we're using a power output tube. This could be either a triode or it could be a pentode, as in this case, where the screen grid is connected to the plate supply through a resistor. Normally this would also have a bypass capacitor and other things. I'm only showing this as sort of the bare minimum of the output circuit, for example, of a Williamson amplifier. Over here you have the output transformer, and in series with this plate lead is an inductance. Now this is the leakage inductance. It's not actually present. It's not physically there. It's actually a representation of what's going on inside this transformer. But here is the problem. When this tube turns off, remember this is a class A-B stage, so it's on for part of the time and it's off for part of the time. When this tube turns off and the magnetic field in this transformer primary collapses, most of that energy is transferred to the speaker, and it's what's called damping. In other words, the induced voltage in the primary due to that collapsing field is coupled to the speaker and is therefore dissipated. This is a damping factor, which we haven't talked about, but it's an important characteristic of amplifiers. But because not all of the flux from the primary makes it to the secondary, some of that collapsing magnetic field produces a reverse EMF, that is a reverse voltage. And we model that by putting this inductor in series. This inductor is not magnetically coupled to this transformer. It is a fiction that we are using to create a model. And this is where leakage inductance comes from. And you can determine how bad a particular transformer is going to be with regard to leakage inductance by some measurements that I'll show you in a second. But the important thing about the leakage inductance is it occurs right at the time that the one stage is turning off and the other stage at the bottom, if this were push-pull, is turning on. And the problem with that is it induces an additional voltage into a tube circuit that is not present generally in transistors. Now that doesn't mean that transistor AB amplifiers don't have crossover distortion. They do. But tube amplifiers using output transformers have additional crossover distortion due to leakage inductance. So suppose we have some transformers and we want to know which ones have the most leakage inductance. So on the bench I have a transformer. In this particular case it's a power transformer, and normally it's connected by hooking the 110 volts to the primary over here, and you get 25 volts between the two yellow wires, it's center tapped. So basically it's a 12 volt center tapped output. But I'm going to use it to demonstrate how you measure leakage inductance, also how you measure inductance in general. And I'm going to be using the Atlas LCR meter. So let's turn that on. And I have it connected to across the full primary, or in this case, it's the secondary. If it's a power transformer, I'm going to call it the primary because transformers are relatively symmetric. And you notice that it reads 29.03 millihenries. Now I have shorted the secondary in this case, and I'll continue to use the nomenclature of primary secondary so it fits the picture we showed in just a few minutes ago. So I have the secondary shorted. Earlier when I measured this, I measured it with it open, and it basically measured the inductance of the primary. Now we're going to measure the inductance of the primary with the secondary shorted. And you see we get 1.952 millihenries. So earlier we got 30 millihenries. Then we got, with the output shorted, we got 1.95. So I'm going to call that 2, and I'm going to call the original value 30. So the ratio of inductance in this transformer is about 15:1. And that is of the primary inductance to the leakage inductance. Now that generally is a good measure of the efficiency of the transformer. So 15:1 means that 1/15 of the power is wasted in the transformer. And that's only approximate. One reason is this transformer was designed to operate at 60 cycles. This meter measures at a kilohertz and so on. But basically you're getting a measure of how much the leakage inductance is in this transformer. Now, suppose that you also want to know what the turns ratio is. Well, we know that the primary inductance is about 30, so let's measure the inductance of the secondary with the primary open. So now, leaving the primary open, I have connected the inductance meter of the LCR meter to the secondary, and we'll analyze that. And we get 516 millihenries, 516.6. So now let's do some calculations. So what I've done is I have divided the inductance of the secondary by the inductance of the primary. And then I took the square root of that ratio, and I get about 4.14. This is the turns ratio of the transformer. In other words, the turns ratio is approximately equal to the square root of the inductance ratio. Now, we know this is a 120 volt transformer, and it's supposed to produce about 25.6 volts. Actually, it's a little higher than that. It's more like about 28 volts. But the nominal is 25.6. So the nominal turns ratio specified by the manufacturer is about 4.68. The voltage ratio between the 120 volts, in this case the primary, and the secondary, is the turns ratio in a power transformer. So now we have a pretty good idea of what kind of transformer we have here. We have a turns ratio of somewhere around probably about 4.5, and with an impedance on one side, an inductance of 516 millihenries, and an inductance on the other side of 30. Now, once we know this, we can compute a number of other things. For example, if we put an 8 ohm speaker on one side of this transformer, we can calculate what the reflected impedance would be, that is, what the tube side would see looking into the transformer, with an 8 ohm impedance, and so on. I'm not going to go into that because I'm primarily focused here on the idea of leakage inductance. But nonetheless, by using a simple inductance meter, you can get these sorts of knowledge about your transformer, your output transformer, a power transformer, any kind of transformer. Now what I'm going to do is I'm going to repeat the measurements, but using a different meter. Now I'm using a Pros Kit MT5210, and it is set to measure inductance in the 200 millihenry position, and you notice we're getting 28.9. Now contrast that with the Peak Atlas that gave us about 30. Now let's come over and measure the other winding using this Pros Kit. And I had to change the scale to the 2 Henry scale because the inductance on the other winding is more than 200 millihenries, and I'm getting 510 millihenries. Remember, we got 516 with the Peak Atlas. So very close to the same readings. Now let's try that leakage inductance measurement using this Pros Kit meter. And so I've shorted the second winding, and I have the meter still across what I'm calling the primary. You notice that if you remember, the Peak Atlas read 1.56 or so millihenries. This meter reads 2.33. So what are the differences? Well, these two meters actually operate a little differently. So the difference is not significant. But if you remember that you take the ratio of the inductance with the output open to the inductance with the output shorted to calculate the relative efficiency of this transformer. Because the leakage inductance is a little higher now, instead of about a 15 to 1, we're getting about 14 to 1 in terms of the power transfer. So about 1/14 of the power is wasted compared to when we measured it with the Peak Atlas, we were wasting about 1/15. Now, those differences are relatively minor. What I'm now going to do is try a different transformer that has, once again, similar characteristics, just to show you that you can get pretty reliable readings on any transformer. And here are the two readings that I get on this new transformer using the tapped yellow wires. And you'll notice that it reads 39.7 on the Pros Kit and 34.9, or we'll round that up to 35, on the Peak Atlas. So you can't take these inductance readings with meters like this as absolute. There's considerable variation, and it varies depending on the circumstances. If you have a lot of 60 cycle floating around your lab, that'll get into the measurements, and it's not a very precise way to measure these transformers. But for a person who wants to characterize some output transformers from their junk box to use in tube amplifiers, it's a pretty good way of determining about how much of an inductive kick you're going to get from that leakage inductance. And that can help you in designing the stage. We won't go into the actual design of stages for this sort of situation, but if you're interested in that kind of thing, I suggest two books. If you're more into vintage, then I would suggest using the Radiotron Designer's Handbook. This particular one was published by RCA. It's the 4th edition. It's by Langford Smith. There's a real good description in there on leakage inductance and output transformers. Another modern book is Valve Amplifiers, the 4th edition, by Morgan Jones, published by Nunes. This is a really good source if you want to look at amplifiers, tube amplifiers, from the modern perspective. This is a good book to buy. It's a little bit expensive, but I think well worth the money. There might be a version available online. I know there was a third edition. The third edition is substantially different from the fourth. There's a lot of new things in the fourth edition. So I suggest if you're going to buy one, be sure you get a fourth edition. But you might be able to find this online, I'm not sure. At any rate, those are a couple of good books that go into subjects like this in more depth than I can in a short YouTube video. But I hope you've enjoyed understanding a little bit of why it was that McIntosh went to so much trouble with the output transformer and actually designed a new transformer using the cathode circuit of the output tube in addition to the plate circuit, cathode coupling, and why by reducing the leakage inductance he was able to produce an amplifier with less distortion. And the distortion was primarily in that inductive kick that occurred when the tubes switch on and off due to leakage inductance. So I hope you've enjoyed this. It may be a little more in-depth than some people would prefer, and so I'm going to leave it at this point. But I do wish you success in your tube amplifier endeavors and wish you for now a nice day.